All right. Hello. Welcome. Hey, everyone. So I hope you're looking forward to putting up with me for a second time. I do believe you have UCHR next Monday again, but I'll be back next Wednesday too. You all looked so depressed on Monday. I don't know what it is. I'm not sure if it's 1531. Put your hand up if 1531 is why you're sad right now. Okay, got like 4 hands. Put your hand up if something else is kind of crappy in life right now, but it's not 1531. Okay, it's like a 50-50 split. That's really promising, isn't it? Well, today we'll hopefully try and turn some of those frowns upside down by talking about a mildly more interesting topic. We do have our friends joining us from online here. As always, we've got our Slido. You can join that. Didn't seem keen last time, but we'll see if you're any different this time. And our YouTube chat, so you can kind of keep tabs with things. For those people over here, I will get rid of this after like 5 minutes, because I know that's like impossible to see. But we'll just like leave that up for a sec so people can kind of settle into it. All right, so Lecture 4.2, HTTP servers. Probably one of the, I don't want to call it the most exciting lecture, because that kind of implies as if like this experience right now is particularly exciting, but it has probably some of the most memorable content for you in the course, which is that we're going to talk about how to write a simple HTTP server with Node.js. And there's many different languages you can do this in, and there's other cool stuff, but for a lot of you who've done, 1511, maybe 1521, maybe 2521, a lot of your comp sci degree to this point has been just kind of like writing little programs and running them on something quite small, and like unpractical. What I mean by that is you've maybe written some stuff in C, right? But when you go do a course in 1511 or another course like that, you never really sit around being like, oh my God, I'm like writing that thing that I was like using 3 years ago or something, Like, has anyone here done 2521 before? Yeah, so like merge sort, quick sort. You've never sat there learning about that being like, I get it now. I get how Netflix works. There's like that kind of lack of connection. That's not to say it's not relevant there, but what's cool about the topic of building our own web servers is that we all work with web servers every day. This website's a web server. The course website's a web server. That's a web server. That's a web server. Like it's everywhere. Because you think about, I always kind of challenge people. Think about what you do on your laptop now. Who uses Google Chrome here? Hands up. Yeah. You don't give a shit, do you? So if you think about your computer, whether you're using Google Chrome, Safari, Firefox, whatever, that's mostly what you're using now, on your computer. It's mostly that. And tell me some apps, just do your best to contribute. Tell me an app you use on your computer that isn't based on like Chrome, Safari, or Firefox. That you have, like if you're on Mac, you've got the little thing at the bottom. If you're on Windows, it's the same taskbar. Something down there that's not a web browser. Yeah. File Explorer? Yes. What else? Just want 2 more. Steam? Yep. Steam. Yep. Teams. Okay, cool. Now what's interesting about those examples is like Steam, that's the video game thing, right? Yes. And then File Explorer. Those two have nothing to do with web servers, but you mentioned Teams before, right? Most of you should be using Teams by this point, I imagine. You've been playing around with Teams. Teams is actually built as a website in disguise. If you go to teams.com or whatever the website is, teams.microsoft.com, I don't know, you will notice the experience is the same. And that's because what Microsoft do with something like Teams, and many other companies do this, Discord's the same, they build like a website like Teams, and then they literally kind of take that website, they go make an app, just like File Explorer or Steam or something else, and they basically make an app, and all it does is it basically runs Chrome in the background, but it gets rid of all the Chrome stuff, and it just leaves the web page part, and it just runs Teams in there. That's why Teams doesn't work without the internet, but other things like File Explorer or Steam might work a little bit without the internet. It's because it's just a web browser in disguise. And the reason I'm pointing that out is because whilst we're talking about web browsers or web systems and why they're so important, I want you to realize that they're probably even more important than some of you would consider, because nearly everything we're doing now is based on them. when I say nearly everything, I mean at least 80% of it, right? Emails, calendars, Teams, Discords, like so much stuff is just on web. So it's a really important topic because I mentioned last time about how many of you would end up being JavaScript, developers in some way, but I would hazard a guess that a solid 50% or more of you, more than 1 out of 2 people in this room, will end up working with web servers in some way, post-uni. And it's a big part of software engineering these days. It's kind of synonymous, right? And whether you're like actually working on a server, whether you're building a front end, I have friends that work in cybersecurity. They don't do any like deving or programming, but they're constantly testing web servers, because nearly every product's a web server. So it's super, super relevant. I've kind of covered that in this slide, but there's some of the things that we're going to talk about. We're going to do like 5 or so minutes of some general background on web servers before we go deeper. We're going to talk a little bit about terminology. You'll see 3 terms up on the screen: network, internet, World Wide Web. You've probably heard them all before, naturally. It's important to distinguish them and contextualize them within one another. Networks are just computers connected together. You don't need the internet for a network. If the internet's down and you're at home and everyone at home's on the same wireless router, you're all still on the same home network. It's just that home network can't talk to the internet. That's how you can maybe share files at home. Or does anyone have like a house printer? Anyone got like one of those printers you like print to? Yeah, 2 people, cool. That's all on, that's all just in a network. Has nothing to do with the internet. If the internet wasn't invented, you could probably still do a bunch of that stuff. The internet, though, was the global network of computers. So rather than just all of our homes be connected together in isolation, it was like, let's connect them all together, and that's how computers from all around the world can talk to each other. If you really spent some time, you could actually get your computer up on the internet that someone could type in an IP address and they could actually access something that you've made on your computer. A couple of you in here have probably done that because you're little hobby computer scientists. But it's all kind of possible. The world's quite connected together in that way. And then we have the web, or the World Wide Web, which is like what your maybe like your grandparents or like older parents might call the internet. Be like, oh, what are you up to on the World Wide Web these days? But it's a term that describes, and I think this nuance is really important, a system of documents, resources linked together, accessible via URLs. And this is an interesting idea because if you think about it, what is the internet without a URL? Because think about all of your interactions with the internet, right? If I say, how do you use the internet? Think of a time, can someone even tell me what's the time you use the internet without in some way using a URL? Yeah.
To use an extension that I installed.
To use an extension that you installed, like on Chrome or something?
Yeah, something like that.
Right, so because it's installed, and once it's installed, you don't need the World Wide Web. Is that what you mean? Yeah, so that's an interesting point. The funny thing with that one, of course, is that there was probably a URL somewhere that you went to get that extension, right? But you're right, once you have it, you don't need it, which is a good point. Really simple example for you all. SSH, right? You never typed in a URL. Obviously, there's like .csv, but that's not a URL. We'll get to that in a sec. It's like SSH is something that has nothing to do with the World Wide Web. So if you're doing something on a computer that directly or indirectly is related to using some kind of browser and putting some kind of URL in that browser, that's the World Wide Web, and it's a part of the internet. It's a massive part of the internet. For most of us, it's kind of what the internet broadly is. And even you think I load up Teams, there's no URLs there, but how Teams will actually be working behind the scenes is that Teams is loading up web pages in the app, and then when you send your request, it's actually calling URLs behind the scenes anyway. So there's a bunch of stuff that might not even seem like it's doing things with URLs and web browsers, but it all kind of is behind those scenes. That's about as deep as we get into networks here. So if you want to learn more about networks, you can go study 1531. I don't believe it's compulsory, but it is a fairly common elective. I did not take it when I was an undergrad here. I have mixed feelings about that, so you'll be fine either way. I have lots of friends who've taken it and were like, that was a waste of time, and I have lots of friends who took it and was like, thank God I took that. I would probably say generally when it comes to this network stuff that if you feel like you're ever going to end up in a kind of career trajectory where understanding the nuance of networks matters, a good example is cybersecurity, because most cybersecurity these days is web-based, again, then I probably would do networks because you do learn a couple extra things in that. But then there's other people I meet who are just like hardcore, I want to be like an algorithm designer or I want to, work just on like making cute UIs at Canva or something, and maybe it's less relevant there, but you can go look at that if you want to. Okay, so network protocols. Over any network, home network, World Wide Web, the internet, whatever, to communicate over those networks, you need to have some kind of structure. This makes sense. We have structures in all kinds of protocols. Does anyone want to tell me a protocol you can think of that has nothing to do with computers? Yeah? Fast charge protocol. Yeah. I'd say that's a little bit software-y, but I like that it's not, some boring computer thing. Yeah, so like how to phones and chargers or cars or whatever figure out how to fast charge, right? Because there is actually, like, you think about USB-C. When I plug my phone into a PowerPoint, the phone and the USB-C actually have to talk to each other, and they kind of say like, hi, and then they kind of figure out, what can you do, what can I do, what can we do together, and then they figure out what to do. If anyone has a MacBook and you have a friend with a MacBook, has anyone ever tried to like plug in a USB-C into both MacBooks and see what happens? Yeah, am I the only one with a morbid curiosity? Okay. One of them will charge each other. So if you're out with a friend and you have, and this will probably work on a bunch of new Windows too, is like if you're out with a friend and you have a USB-C cable, you can actually charge each other's laptop if you want to. But the interesting question is which laptop charges which, right? Depends which way you plug the cable in, but that's a protocol. There's a set of rules that dictate how a kind of interaction goes. And networks are the same, humans do the same, handshakes. When you're on the phone to someone, you don't just call up your parents and say, what's for dinner? And they say bacon, and then you hang up, right? You say like, thank you, goodbye, probably, and then you hang up. So there's protocols everywhere. So different things in networks have different structures and different protocols. Here's a bunch of network protocols. I know that diagram's quite small, but it highlights a few things like, I think SSH is not there, but it kind of is. Some other ones you might have heard of. There's a middle column there that has email. That is like SMTP, POP, and IMAP. I'm sure a bunch of you have seen those words thrown around before, SMTP, POP, or IMAP. They are basically email protocols, because back in the day when emails were less in web browsers and they were more downloaded to the computer, you needed a certain way for like your Outlook or Gmail that was running on your computer to know how to talk over the internet and how to do things. But a really common protocol that we're going to talk about a lot is the HTTP protocol. The HTTP protocol is the protocol of the World Wide Web because HTTP is the structure of URLs. That's why all of your URLs you have start with HTTP. It's not particularly astounding, but it's just an example of one of those protocols, and it's what we use with web browsers. I have another few applications here. The bottom one's SSH. This is like a Windows SSH client. This used to be used a lot in CSE before VLab was invented. VLab was set up. Invented's a bit dramatic. There's an email client, and then the top one there is an FTP client. So has anyone heard of FTP before? Yeah, a very small number of people as well. FTP stands for File Transfer Protocol, and it's just a way that people set up that you could send files from one system to another without having to go through a web browser or a website or a web server. You would just kind of type in someone's address, you would connect to them, you'd have like an open line, and then you would just be able to transfer files back and forth. Again, less popular these days. Everything seems to be converging back to HTTP. Here are some more examples. This is from a blog called bytebytego.com. It's really interesting stuff. They do an amazing number of infographics out there. But they kind of show you here how different types of protocols behave in different ways. A question that always comes up, what's the difference between HTTP and HTTPS? Because if you pay attention to your browser, you'll notice that HTTPS is everywhere. I'm not even sure if there it is, hiding up in our URL. HTTPS is the secure version of HTTP. When we talk about HTTP in the course, we are kind of broadly talking about HTTPS as well. They are kind of the same protocol. It's just HTTPS has basically like a quick check to make sure someone is who they say they are. Because the way HTTPS works is that you're over here, you're trying to talk to something over here. Maybe it's Netflix.com. You kind of say, hey, are you Netflix.com? Prove it. They prove it. And you go, OK, I trust you. And then you too can see the data. But all the data that you've shared in the meantime, anyone kind of listening or on the network, they kind of can't see it, right? Because before HTTPS you could. And what I mean by that is like you go back 10 years before there was HTTPS. You at home, if you have, does anyone have a sibling here? Anyone have a sibling they don't like? Shy hands. So like you could, if you're on the home network, you could actually just like listen, you could actually just read what they're sending over the internet for a very long time until like, they started to get their act together with HTTPS, just because you were like on that pipeline between them and Netflix. So HTTPS is kind of the standard for HTTP now, but we still kind of just talk about HTTP generally. So it is just the protocol for sending and receiving HTML documents. Nowadays, it is sending much more typically than just HTML documents, right? It's often doing crazy things like streaming YouTube and Netflix and was it Apple TV? That's the one. But yeah, so lots and lots of different things. But web browsers are still kind of the base of how it's all done. So I've said this like 6 times now. Network, internet, World Wide Web uses the HTTP protocol, which is a way of everyone talking to each other over the internet through web browsers based on HTTP URLs. Well, that's it there. Now we're going to talk about the coding side of things. And this part's where things get a little fun. We're going to be talking about Node.js Express servers. So there's a particular web server that you can use in Node.js called Express. Express is the name of the library. It's like Jest, right? Jest, ESLint, TypeScript. These are names of libraries that people make. They open source them and we can use them. Express is the open source library, probably the most common one for Node.js. There are other ones, Express, there are other ones that might be like more, in software we call them opinionated, or like an opinionated library might be one that like is less kind of blank canvassy and more like, this is how you do this is how you do this, which can be good or bad. And there are also going to be some lower level libraries that don't abstract as much away from you. Yeah, someone's pointed out the slides are cut off at the bottom. Yes, thank you. I'll just try and make that a little better. That should be okay. Cool. I've said it before, I don't understand why MacBooks couldn't make screens to the same size as everyone else. Here's an example, Express server. Interesting piece of code. A little bit to unpack. I got some fun little animations for you to unpack it. Before I go further, this is an Express server that is capable of you sending a request, an HTTP request to it via a URL, 2 different URLs, and depending on the URL you give it, you will get a different result. So in fact, before I go and explain it, let's actually just go and run it. So sorry, I thought I had this folder up before, but I guess not. Again, same as last time, I'm just using last term's code because it hasn't changed. So we're in our 4.2 here, lecture code. I have to do my npm install because we've got all the TypeScript and everything else. You can see this is a TypeScript file. It's a good example of a file that like doesn't have types in it, but TypeScript will still run it, because we always talk about how TypeScript doesn't need those types to necessarily work. But if I try it now, npm run ts node expressbasic.ts, hopefully it should work. It does work. Here's the interesting thing. It works. Oops. But unlike a normal program you might be used to, it doesn't really run and stop. It's just, well, it looks like it's running and stopped, but it's just kind of sitting there running forever. Imagine this like a while true loop. It's just like looping infinitely. And what it's doing whilst it's looping infinitely is it is waiting for someone to talk to it. Now, in this particular case, I'm on my computer and I'm running a web server on the same device, right? In reality, maybe a web server's over somewhere else, in Western Sydney or something. But right now, they're on the same device. And I can talk to that web server very simply, and it's always the same. If I go to the URL up here and I type in localhost, that's the IP address of your own laptop. It's just kind of hard-coded in. and I type in 3000 like that, that's the web server. It's this particular, you might call it like a website, which is just my computer, 3000. And then you'll see here in these app.get lines on line 8 and 12, I have a few different things. So if I just type in /hello there and I hit enter, let's see what happens. I get that. So what's actually happening there is that I am sending an HTTP request, because that's what that URL is there. It's that format. Chrome's very good at hiding that now, because like who really needs to see it? But it is HTTP localhost, something like that. Port 3000, don't worry about the ports too much at the moment. /hello, and I get that. And what happens is that web server got talked to by my computer, and that's the result it gave. I'm just logging back into the chat. Oh, you're not that excited, are you? Should be. This is the foundation of much, much cooler stuff. Well, let's have a look at the code. Let's break down what it's doing here, because I can also change it to this one here, where instead of hello, I can do what's up, and I get that result. Different kind of result, but again, let's talk through the code. So, firstly, I'm importing the Express library. We've imported libraries before. That makes sense. The next two lines are kind of funny. The first one is that I'm making an instance of a server. The Express library itself, like you got to think of it, it's not a server. It like gives you the instructions to create a server. So Express is the library, but when I say const app equals Express, I'm kind of invoking a function, and that function returns me a whole web server inside of app. App would be a gigantic object. Who knows what's in it? We don't really need to understand it, but it is a web server. I'm setting the port to be 3000. We'll kind of come back to that. But basically, computers have like 10,000 different ports you can use, and then you kind of can't run any more web servers on them. Think about it like that. So it's like a bunch of PO boxes at a post office, right? At some point, they run out of space, but there's lots of different like points of connection people can have. This line here is necessary for, it's kind of annoying that we have to write it, but this just tells the Express server to return text. You don't need to worry too much about that. But here's the interesting stuff, because a lot of those top lines and the bottom line too are kind of cookie cutter. You just write them in each time. But this is where you actually program the web server to do something interesting. And it typically follows the format of you write a URL here, and then after that URL, you tell it what it's going to do. And in the case of these really simple servers, what we've done is we basically said, hey, if someone tries to access you with the URL /hello, what I'd like you to do is respond by sending this string. And similarly, if someone tries to access you with URL /what/up, I want you to send back a JSON string that is the JSONified object, you know, key value not much. That's a terrible example. That's what I want you to do. And then the last thing we have, this is just the line that actually starts the web server, because the stuff up the top is just kind of setting it up, creating it, but it's not really running. So this bottom line is like, now it's time to go and run so that someone can talk to you. But that's an Express server. Ghosted Blade on YouTube says, can you only go to the server once you run TS node? Yes. The server is not running until you run it. And similarly, once I kind of close out of it, like once I Control-C here, the server is no longer running. And if I try and load that page, I get an error. Because the browser like tried to talk over the network to something, but there was nothing there. So then the browser's like, it doesn't exist. It's like typing in a random URL on the internet. It just isn't there. But when we run the server again, it now suddenly is there. There's the page. I can close it. Now it's not running as well. Any questions about that so far? My shy, quiet friends? Cool. All right. Now, if you think about just this for a sec, you can do a pretty good job at understanding what I'd probably refer to as the old internet. The old internet is kind of, it's just what I describe the parts of the internet that are just a series of static pages, right? So Wikipedia is a great example because it's kind of the most popular, classic, old internet page that survived. Though I am looking for, and I don't want Wikipedia, random article. The Nuka Hiver Rail. Oh wait, is that a bird? I thought it was a train. No picture though, it's a bit rude. You think they could put a picture here? Interesting. I'll pay ID someone $1 if you go and put a picture on Wikipedia for everyone's sake. But it has to stay up for a week because you can't put some crap there and then Wikipedia editors are like, no. Why is there no picture? That's weird. Anyway, I like to think of this page as the old internet because it's kind of what the internet's been for 20 years. It's like a static page. It doesn't do anything. There's no live chat. There's no videos playing. It's just text and borders and paragraphs and things like that, right? This is like pretty static content. And how the internet would typically work is quite literally you'd have a web server, and what you would do is you would maybe send a request to that web server where the URL might literally or figuratively represent a file on that web server. And all that web server was doing was add a basket of files, you know, unsw.html, usid.html, uts.html, a Wikipedia page for every university, and it would just like send it back when you asked for it. You know, it was like a remote file system that everyone could access. And that kind of makes sense when we think about this code because all you would maybe do here is, depending on the particular URL, you would just give them a different page. And if they wanted to go to a different page, you know what? They put their mouse over subfossil, and you can see in the bottom left of my screen, should be able to see that on the recording, it says, yep, wikipedia.org/wiki/subfossil. Go and fetch a different page. And then the browser totally like dumps that page you're on, pulls in a whole new page, and puts it up on the browser. But just if you were getting comfortable with that idea, nowadays, web servers are used in very different ways, or more, I should maybe say more extended ways, because they still do that fundamentally, but they do a lot more. And how web servers have changed is when you go to a page, a good example is Netflix, right? Who's watched Netflix? Stan, Binge, Prime, Apple TV? Yeah. Has anyone not watched it? Any of it? Really? That's awesome. It means you're a productive person. So if you've seen any of those things, when you type in netflix.com, easy one to pick on, you go to the web page, maybe it's their like home dash screen, you know, with all the movies that you never know what to pick. It's like you probably got some big dump of code that the web browser's rendering, right? But if you pay attention, what actually happens after that point nowadays on most websites is that after that initial page load, you're not really fully loading any more web pages. There's just a lot of stuff kind of happening quietly in the background. If you're not sure what I mean, another good example might be like Instagram.com or Messenger.com or something like that. You know how like you're messaging friends on Messenger or Instagram and they're all just like coming through in real time and things like that? You're not requesting a new document, are you, when you're exchanging messages with your friends? What is actually happening these days most commonly with web servers is that a web page like Netflix or Messenger or Instagram, after that page has loaded, it's loaded once, and then whilst you're interacting with the elements of it, it is quietly, very quietly making little requests to the web server behind the scenes. That's how when your friend sends you like a message every 3 seconds, it's just kind of appearing on your screen without loading a whole new page, because that is being pulled quietly in the background. And why that's important is because web servers aren't just returning pages now, they're actually exchanging data. Because when you get new messages from your friend, it's not going to be a big HTML web page or something. It's probably just going to be a little string, a little string, a little string, a little string. And because it's typically very simple pieces of data or very structured pieces of data, most web servers now, when they're sending that quiet information, that information quietly behind the scenes, they're often doing it via JSON. JSON packets of things, you know, arrays, objects, strings, numbers, like arrays of objects, or objects of objects, or arrays of objects, whatever. That's all happening behind the scenes. What I mean by that is, you know, another good example is like, when you're on Netflix and you click like next, 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 trying to jump ahead, it's trying to pull all that data quietly in the background again. You don't have to refresh the whole page every time you hit next. So the reason that's important is because most servers nowadays, when you're working with them, they actually often respond specifically with JSON, not so much HTML or text or anything like that. Because this page here, this Wikipedia page, if I go and look at it, this is what the web server returned when someone loads the Wikipedia page. That's a lot of HTML and another language called CSS, and also some funny JavaScript that isn't quite the JavaScript we do in the course. It's like this stuff. That's all JavaScript. Horrifying, really, if you think about it. But it's all of like web display stuff, like web UI languages. Whereas all these things that are going on in the background, they're typically responding with JSON. And we can make our web server respond to everything with JSON simply by making these two tweaks, which is that line we had that said app.useExpress.text. We actually make that line say app.useExpress.json as it's written on the screen. And instead of saying response.send, which we had in the previous example, we simply now say response.json. And what that basically does is it just stringifies it. Because you saw in the other example, if I pull it up, 4.2 here, see how like before we just used to send back a response that we JSONified the object anyway? This is just like a shortcut. So now we can just say response.json. That's how you send something back with JSON. So now when we have a little web server like this, our Express JSON web server, you'll see that if I access what's up, it's now going to send this back. Now that looks like text, but that's just the browser displaying it like text. If I kind of unpack what's happening behind the scenes here, you should actually see that request headers, response headers. It's not really saying it here. Raw. Would have thought it says it. Don't worry about that particular part. But that's all coming back as JSON. Now, typically, it's not getting displayed on the page. It's actually getting like churned up by the front end itself and then displayed back to you in some kind of way. But that's essentially what we're doing. Yeah, cool. So rearranged a bunch of these slides last time to make more sense. So I'm just refreshing myself. Now, a couple of points about this web server. Before I kind of keep going. I'll give you a bit of like a coding break, not that there's been too much. But first point, if you have a look at these functions here, this is actually why we go through that 4.1 lecture before this, because it's worth trying to unpack the new function syntax and first-class functions here, because you're actually seeing it. Because if you think about what's actually happening here, this is a function, right? That's the new function syntax. So how this is actually working is how you write Express code is you actually say, hey, here's my web server. When someone tries to get info on a particular URL, this is the URL. I want you to call this function. And then we say, const function equals this. And what the function does is the function takes in always the same two things. It's always a request object and a response object. The request object is where you pull information that the person calling you has given. Such a good example is like, when you make a comment on YouTube, who writes trolling YouTube comments? A bunch of you, I'm sure. You type a trolling comment on YouTube and you hit send. Well, that data you wrote has got to get sent to the web server, right? That all comes through as the request on the way in. And then the response is the object that you can modify that goes on the way out back to the person who called you. And that's kind of why if you look at, this example here, we don't really do anything with the request in this case, but we do kind of send something back in the response. So there's like an input object and an output object. We don't need to return anything with that function. It's a little bit weird, granted. But again, it does rely on those two things we talked about in the last lecture, which is first-class functions and the function syntax. Because you will always see Express servers written like that. That's just how all the code is kind of written on the internet. So I don't want you to be too alarmed by it. And also, as I probably should have pointed out last lecture too, notice that a lot of your jest code also has that format. And if you pay attention to some of the jest code, and we're going to get into some again soon, but notice how this is different jest code to what you've probably seen. But notice how jest code is actually just a series of describe and then a string and then you pass in a function. So you pass in a function as a first class function, then inside that you say test and you give it a string and then you give it another function. So jest is the same thing in nature. You're just like calling a function that you pass in another function to, and then you just define that. And because it's defined all anonymously, it has this kind of nice nested structure. But that was kind of point one. Point two is on ports for a second. So on your computer, you should generally, when you run your web server, most of the code we give you has like a default port. It's like 3000 or 5000 or something like that. You can broadly run things on any port above 3000. 99.9% chance it won't be a problem. And if it's a problem, it'll tell you. It won't even run, if that makes sense. And you can see this pretty easily where if I run the server here, right, and then I open a new tab and I run the same thing here, which was it? Express JSON, npm run ts node express json.ts. You'll see it will just be like, nah, it's like listen, address already in use. So we basically occupied that particular port on the computer, but if we change that to 3001, we could now run that. Now, who works locally on their own laptop? And when I say that, I mean they like don't use Tiger VNC or VLab at all. Hands up. Okay, who uses Tiger VNC or VLab? Cool, you like me. I like it. So here's the thing, important thing to note with Tiger VNC. When you connect to CSE, right? The CSE, the way VLab works is that VLab are a series of virtualized servers, and there's a bunch of them. And what that means is like CSE has like 20 VLab servers. Let's pretend they're physical devices. They're physical separate servers. But on each of them, they're able to create little mini environments for you to log into. So when you go and connect to VLab, you're basically being given a little mini environment on like an actual computer, and that's the way you do your work. You can tell what actual computer you're given by what comes up here. See how it says VX16 in that particular case? When you're on a particular server, you share the ports with all those other people who have little mini sessions on it like you, if that makes sense. So if you, say, run an Express server on VX16 on port 3000, and another CSE student tries to run an Express server on port 3000, they'll get an error saying they can't do it because someone's already running it. But if they're on a different VLab server, then they won't get that error unless someone else is running it on that server. That's not super important. It's kind of background detail. But the reason I point that out is because if you're a Tiger VNC or VLab user, your chances of having a port conflict go from like 99.9% down to like 20%. But it's not a big deal because all you do is you just look at your code and change the number to like 3001, try it again, 3002, try it again, 3050, try it again, It's really easy to solve. But if you're not sure what VLab server you end up on, it's all kind of, I don't know how specifically they do it, but they'd probably load balance it, where like you would generally get directed to the server that has the lowest load. We keep getting sent to 16 here. But if you try that again in 10 minutes, you might end up on like VX18 or something like that. All right. How servers receive information. So we kind of talked about how servers send back information via JSON, but we haven't really spent much time talking about how they receive information. There are a few different ways that they receive information. One of the easiest ways that they can receive information is via the URL. So in this particular code example here called input query, it's a very similar example, except I'm trying to capture a name and to capture an age by writing this code here, and then I'm simply trying to return that information back. So what this server is trying to do is on the request, it's trying to grab a name and an age that the client sent it, and then it's going to package up a JSON object and send that object back. The request object is where the incoming information is. If you want to access stuff in the URL, it's accessed via the query parameter of the request object. And then on the query parameter, you have all of the queries that you send in. And you might be thinking, what in the world is a query? Well, let me show you. So when it comes to the query part of the request, see, got to close it off. What that is, if I go to, I have to go to my/URL, right? Right now it says name is undefined, age is undefined, because what my code, when it tried to get this, request.query was a valid object, but nothing was in it, because there was no query data. But how I add query data is like this, name equals Hayden. So when you have information in the URL of a URL you're making a request to, that is actually passed through to the web server as a query object. If you want to add more stuff to the URL, you simply add more with an ampersand in between it. And I can add more in this case, like height equals 20, except and all that data would be coming through to the server. So the name, the age, the height, it's all channeling through to the Express server. However, the Express server is only using 2 of them. So kind of the third one, the height's just kind of getting thrown in the bin. And the Express server is then packaging that up in an object and sending it back to me. So that's how we can send data through to a web server. This is pretty common. My favorite example of this is usually Google Maps. And the reason I like Google Maps is because it's very complicated how they do it. But a long time ago, Google Maps didn't used to have this. But let's say you're like looking around and you come into Marrickville here and you see the Samola Sydney Italian restaurant. And then you say, oh my God, I really want to go there for dinner. It looks expensive. Let's go with my friend. So what you do is you click on the URL and you copy it, right? And you paste it to your friend. Who's done that before? Yeah? I know you have. What this is all of this information here is actually, it's a very weird Google codified way of doing it, but Google is capturing information in that URL so that when you, who's never been to that web page, get that URL and load it, the server actually gets that input information to know exactly where to send you when the page loads. You never really think about it. It makes sense when you think about it for like 5 seconds, but it's like, oh, okay, so all that URL, and you can pick up on the trend then is that information in the URL is simply a way of like passing variables between people, if you think about it, or bookmarks too, right? Because if I bookmark that page, the bookmark is going to be the URL, which means I can go look it up later. If you pay attention, notice the URL change as I move around, little bits. Notice the numbers change. That's the lat and longitude and the zoom level. So as I zoom out too, you'll notice that that little number changes slightly. So I could, for instance, manipulate that and be like, you know what? I don't want to be zoomed in so far, so I'm going to go change that number from 18.99 to 10. Then I'm just going to get the same page but super zoomed out. Because they're all just input. Like think of the web server, that loading as a function, and they're all just inputs to that function, and then all that's being passed through the query. Again, how Google's doing it's a bit more complicated. This stuff you see here is them probably basically compressing a lot of information in. Because you could imagine Google Maps has got a lot of complex stuff about whether you've expanded this or you're here or you're there. So rather than create like a really, really long URL, they'd have a way of just like compressing it down to something quite small. Because they would be able to unpack what in the ungodly world some of this means on their end. But that's what's happening there with servers and stuff. Let me just see. Okay. So servers can also receive information. There's a typo here. That's why I got messed up. That shouldn't say servers can receive information through the URL. It should say they can receive information not through the URL. Because if you don't want to send information through the URL, you can actually send it through something we call params. And params is like it's basically sent quietly with the payload. Because obviously when you request the URL, you're sending this URL to a server, but you can also kind of tack on a bag of information and send it alongside that URL. It's called params, it's not called query. The code's pretty much identical in that case there. But the thing is, like firstly, why would we not want to send something over the URL? Yep. Yeah, I don't want it exposed, right? So a good example is like a password. That's like the classic example. you're signing into a website. Well, when you hit the login button, what's actually happening is your computer is sending a request to a server with your login details. And then the server's going to determine if it's you, and then you'll get a response back saying, yep, that was you, continue, proceed. But if you send that information over the URL, that's not very safe. And the reason for that's really simple. Even though web traffic's encrypted, as in all that, remember I said that like bag you attach to the URL and you send it along? Even though that bag's encrypted, URLs are not encrypted. I think this is a really important just general knowledge point here, because there was that whole thing a while ago about, the government, recording everyone's internet traffic and stuff. And to unpack that further, for those who weren't like paying attention, I guess, not that you should, it should have to. What that means is that the government, as far as I know now at least, they're recording every single URL you ever send on your computer, but they cannot see the payloads underneath that. No one can. It's like encryption, right? Like the government can't just like decrypt stuff. Like maths prevents that, basically. Maybe the NSA can or something, I don't know. But the government, Australian government, at least to my knowledge, doesn't just have the ability to break all encryption. So when you're on Instagram, as an example, let's say you're sending messages to a friend. What the government captures is the URL, because the URL probably says like instagram.com/chat/send and then your friend's user ID. But then the information in the message is probably sent as like a params, as that bag underneath, that is like encrypted. So like, for instance, if someone's monitoring your web traffic, even though it's encrypted, they could probably figure out that you're messaging this person, but they don't actually know what you're saying to them, this isn't me kind of getting political. I don't really have the time to think about it that much. But I remember this was really well summarized by someone who was like, because when people were kind of talking about the caution of like the data monitoring laws and stuff, they were like, we know you went to a mental health crisis website at 2 a.m. and that you used the chat, but we don't know what you talked about, was kind of the example. And I think for me at least, that's just as like, digital responsible people, I think that's the thing to keep in mind when it comes to this stuff, is all that URL things are always, you kind of got to treat them as public, but the stuff that's being sent with it is hidden. So you kind of got to think about that, if you're, say, doing something on like public Wi-Fi or whatever. Like people, if you're on public Wi-Fi, people are scared of public Wi-Fi. Like, oh, don't connect to it. It's like 99% of the time, if you're sending stuff to your friends on public Wi-Fi, it's like it's all private. It's not like someone's just like reading it all. But you can probably, if you try really hard on like not so much a uni-wide, but if you go over to your friend's house, you could probably easily track all the URLs everyone in that house is sending. So the reason we don't just send everything over the URL is because the systems we have, the protocols we have, mean that it's not strictly hidden away. And we need to hide stuff. And this isn't some weird, dodgy thing. It's like there's just passwords, basic things you need to hide all the time. Even a really good example is, I always tell this example, I did some like IQ test years ago, like a long time ago, and I noticed that the results page, it said like, iqtest.com/results, and then in the URL it was like this. It said like IQ equals like 105 or something. And I was like, interesting. And I just like changed that to like 180 and hit enter, and the results page just changed and the number was a lot higher. And then I sent it to all my friends and was like, yeah, look at me. I'm so smart. Wow, that's an actual website. I just made that up. So, sometimes we don't expose stuff in the URL, not because it's like a password or something secret, but just because we don't want people to break our applications, meaninglessly like that. Yeah.
Some privacy-focused browsers have that HTTPS option.
Yep.
Does that limit the amount of information in the URL?
I don't know if it limits it so much. It's more like the HTTP one, the URL is visible and all the payload is visible to anyone listening. The HTTPS hides the payload underneath. Yeah.
So if someone knows how to decrypt it, they know all the secret stuff.
Yeah, if someone knows how to decrypt it, then yeah, they could read the payload stuff as well. But generally speaking, the way everything's set up is if you're trying to talk to, again, Netflix, only you and Netflix access that. And anyone who captures it in the middle, the only thing they can see is the URL you're trying to access. Because the URL, the other way to think about it, it's like when you send mail. Like you have to write the address on the front. Anyone who sees your mail in the postage knows who you're sending it to. the return to sender and the address, but they don't know what's inside the envelope, right?
How the hackers do it?
How do people get into that payload, you mean?
Yeah.
I mean, firstly, I know I sound loud up the front here, but I don't know an extensive amount about it. But, you know, one ways they might do it is by convincing you or pretending that they're Netflix. They can like make a fake certificate and a few other things and like trick you to being Netflix. But that's very, very hard. I also know that like certain, like, I don't know a lot. Like as an example, I was told by a friend, it's like, you know, if you go into some countries, unnamed countries, like the way they set up their Wi-Fi and certificates there is like they basically, you know, can fake it enough that they can like tap into your data if they want to. But generally speaking, if you're just like day to day in this country hanging about, it's pretty hard to get like hacked these days. Like I don't ever really hear about it just because the systems are pretty robust. And browsers are really picky now. Like as an example, Google started doing a thing some years ago where they basically don't even display non-HTTPS websites in Google anymore. They put out a big notice and they were like, if you have a website that's not secured with HTTPS, we're literally just like not even going to let people go to it. You've got like 2 years to fix this, and then after 2 years, we're just like cutting them out. I don't know if they cut it out fully, but I think they did. But lots of little things like that stuck up, which make the internet pretty safe.
I want to make something that like plans like a holiday itinerary, right? Like
Yep.
I use Google Maps. I can't just like get the links. I can't read that data right in the URL. So like how do those websites do something like that? Does that make sense?
I don't fully understand. So you're saying if you're making a trip, like I'm going from A to B to C.
Website that makes like some sort of itinerary for you.
Yep.
Like a holiday.
Yep.
And like you paste the Google Maps links. Like I want to go from here to here to here. Those websites can't just read that URL.
Oh, they probably can. I mean, I used this word encrypted before just because colloquially people kind of associate encryption with like randomizing stuff. But the correct term is probably more, it's probably encoded data. So as in, because you can't really have encryption without a password. You know, like Google can't just like give that to you and then, I mean, you kind of can, but there's a good chance this is just encoded, which is a way of saying, you know, let's try and express the same thing in like less space by using even more characters. Because like if you think about like a location, all locations are just like A to Z, right? But if you use like semicolons and exclamation marks and stuff, you could theoretically express it with less space. So I imagine, I don't know, I'm just guessing here, but I imagine that's just encoded a certain way. And if you Googled it, there'd probably be someone or a library that's like decode the Google Maps, like location info. Probably, but honestly, it's actually like this is the actual location and zoom thing, and this is the name of the location too. So a lot of that information is still pretty visible in that URL. So point of all that was we'll take a break soon. Let me just get past this bit. The point of all that was to basically really articulate that there's a way to send data through the URL and there's a way to send data not through the URL. And the reason that I had to point that out is because you can't, with Google Chrome, casually send that payload information as kind of casually as you can put data in the URL, right? Because you saw me putting data in the URL. But when it comes to, I wonder if I can, what was that? Do I have it installed? No, I don't. Okay, I'll just do it on VLab. So if I just jump into VLab for a sec, we have these tools and we call them API clients. And the reason we call them API clients is because they are clients that help us talk to APIs. And you can run it on your VLab just by running 1531 arc. And what it does is it loads up a tool. And there's many tools like this. There's a few out there. There's others. I think two of the most common ones I hear used are Postman and Insomnia. But they're all kind of the same. This is me playing around with it from a previous term. But they're essentially a tool that lets you make HTTP requests as if you're a website like Instagram sending messages and other things behind the scenes. So they kind of mock an actual front end. And these things have different types of messages you can send. Because in the early examples we gave you, all of the requests were, you'll notice they were all of this kind of, actually, sorry, yeah, that's not quite what I mean to do yet. So I kind of need to start this up on 4.2. Sorry. I need to do this on VLab now. I think this is also a good point. One really common area people get this mixed up is they'll go and run their like web servers on VLab, but then they'll try and like run the API client locally, which doesn't work because your computer and VLab servers are like two different things. They're not connected. They don't understand each other. So because I want to kind of use this API client on VLab, I need to go run my code on VLab. In particular, the code I want to run is this one here, input params. Should be there. Yep. Node input, npm run ts node input params. Hopefully I have npm installed. I haven't. That's because I have an npm installed. So it's like, I don't know what ts node is. You haven't told me. Express is a bit of a big library. You'll notice this too is like as you get deeper and deeper in these libraries, they can get really big. A lot of like modern front-end libraries installed with npm will get up to like 500-600 megabytes, which is pretty crazy. Like there's a front-end course I teach, and if I was to go and like install every one of the students' stuff on my computer, it would consume typically like 300 gigabytes of space to try and get every like single front-end running at the same time. So it's pretty immense, because Yuchao would have talked about the node modules folder, right, with the npm stuff. Did she show you how big the folder gets? Yeah, cool, great, excellent. So you're across that. So once I run this web server, I can basically construct a request here. We're all just doing get requests for now. And if I was passing information through, it says my URL. Sorry, params isn't, my bad. I got this one mixed up. OK, I jumped ahead. Apologies. Just what I said is still relevant, but there's actually three types of, there's query params and there's body. When I've been talking about that payload, I've been talking about body. I misread the slide. These two are through the URL. There are two different ways through the URL. That's all URL there. And this one is like what I call payload, that like hidden behind the scenes one. So if I just take a step back and I just have a look at this particular one here, because we kind of looked at this example, right, before, the query one, name and age to take you back. That's this one here. This second example, instead of using query, we're using params. And params is just another way of expressing information through the URL. So if I run input params here, input params, instead of doing like this, you actually just do something like this. It's a little bit funny. It's basically the same thing. It's just instead of doing the whole question mark thing and then a list of information, you actually can just like embed it directly in the URL too. I would refer to this stuff as it's purely visual, if that makes sense. Like it has no functional difference. It's not more secure, less secure, this or that. This stuff wasn't around 10 years ago again, but it mostly has come to light because people like URLs that look nice and clean like that. And you'll see this a lot on websites, as you might go to a website, even like Google's a good example. Notice how they've just like structured this all with slashes. There's no question mark here. It's all just like /data/data. Google search engine has generally been quite accommodating to URLs structured like that as well. So because of that, it's kind of common. But they're both basically the same thing. One's called params, one's called query. Anyway, the reason I have to apologize for that is because what I was showing you here, if I jump ahead, God, where's the example for it? One sec, I've definitely skipped over an example somewhere. Oh, yeah, it's right there. Sorry. So the other one, though, is... No, I don't know where it is. Doesn't matter. We don't need the stupid slide. We can make one ourselves. The other type of code that you'll see, if I open up our input params, is it's not params. It's actually called body. Body takes in no information via the URL. right? So params query over the URL, body's that payload behind the scenes. Everything through the body is encrypted. When you send stuff through the body, though, one of the tricky parts is that you can't just, again, put it in the URL, and because you can't put it in the URL, you need one of these API clients to do the job for you. Normally, I would just put it up here, my URL, and then, Hayden, like this. But if I'm going to send it through the body, I go to one of these clients, and what I then do, can't really do that here. Ignore that for a sec. What I then do is I typically have to click on body here, and then I might go and write some stuff, typically JSON here, like this. Most bodies are kind of sent as JSON, and I get that kind of response. Now, I know I skipped a few little tidbits there. We'll definitely kind of unpack that more. But this body is now that hidden payload. It's encrypted. It's private. It's not through the URL. People can't tamper with it. It's just a different kind of way of sending information across. So in summary, you have your query and your params, and then you have your body. Now, if you just bear with me for a few more minutes, we send it through the body. Because we're sending it through the body, we can't easily do that with Chrome, so I needed to download that API client app. And this is where we were talking about API clients are a way to talk to servers. This is the same app, just an older version of it. They change a lot. There's different ones. I use different ones depending on my needs. The one I use at work is called Insomnia. The one I use here is ARC. I use ARC for 1531 because I think it's the easiest. I don't think you do much complex stuff with this, and it's just lightweight, it's easy, it's quick, there's no BS, there's not lots of extra knobs and settings, but you can use largely anything you want. The reason we have to use one of these is because web browsers are always making GET requests. That's what they are. They're basically, in terms of the UI you have, they're a GET request machine. So if you want to make other types of requests, you need to actually use an API client as well. We'll talk about the different types of HTTP requests in a sec. But for now, have a short break, and then we'll get back to it. Okay, let's go. So let's just quick recap, not that we need to from 5 minutes ago, but we've shown how we can create a web server. We've shown how we can kind of capture information from the client in that web server, and we've shown how we can do that via the URL with query and params, and we've also shown how we can use this API client to do it via body. The next thing to talk about is to unpack the other part of that, which is what we call HTTP CRUD methods. CRUD methods are 4 different types of methods associated with HTTP requests. They can either be GET requests, POST requests, PUT requests, or DELETE requests. Each have their own meaning about what a particular API call, what a particular server call is trying to do. You might have a server call, a good example, let's say again, you're sending an Instagram message to a friend. If you're sending someone an Instagram message, you're creating new information. So that might be a POST request. If you're trying to pull information from Instagram to populate your feed, you're trying to read some information. You're not creating anything, so that's a GET request. If you edit a message you sent your friend, changing the contents of it, because you're updating a message, you're not creating anything new or deleting it, and you're certainly not just reading, you're changing something. That's like a PUT request. And then if you're actually going and deleting a message or deleting a post, then that might be a DELETE request. So there are 4 types of requests that you can make over HTTP. In reality, there's a lot more. But each of these requests generally has some different properties to it. When you make a GET, PUT, POST, or DELETE request, all of them are comfortable receiving information via params. That was that one where we encode information in the URL. But where the difference kind of is that GET requests and DELETE requests, you will typically send all of your information via the URL, whereas PUT requests and POST requests, you will typically send all your information via the body. And when I say the body, I mean like what we did back here. Now, that actually makes a lot of sense because, like pretty much all the time, most of the sensitivities of you working with the internet when you're sending information or when you're asking to create or update something, because you don't really need to do much else. But what is interesting is that no matter what type of method you're using to talk to an HTTP server, you will typically always respond with some kind of JSON. So whether you're using like a GET, POST, PUT, DELETE, all of them will end the same way, which is response.json or response.json. So no matter what method you have, it's always response.json. Here's a little infographic you can check out in your own time too. Now, that little GET, POST, PUT, DELETE stuff is this thing here, where we said app.get. You've probably seen that app.get in a bunch of examples so far. So if you want to do a POST request, it's app.post. If you want to do a DELETE request, it's app.delete, app.put, app.post. Post, put, you get the point. They all kind of look the same. What's really, I think, tricky to understand about this, for me at least too, is that the GET, PUT, POST, DELETE don't really mean that much to a computer. Like, they're obviously names, and the computer will send a POST request or a PUT request, but the computer doesn't do a lot of checking. It doesn't like, if you create a GET request that deletes something, right? Like if you have a part of a server that is capable of deleting an Instagram message, and you make it a GET request, like no one cares. The server doesn't care. Most of the kind of GET, PUT, POST, DELETE methods are about communication to developers and stuff. So a lot of this I would generally describe as it's largely best practices. There are a couple of things that might catch you. Like you will notice that if I come here with a GET request, you'll notice that the body actually vanished. I'll change that back to POST. You'll notice the body appears. So this API client won't actually let you send body information over GET, but it'll let you send it over POST, it'll let you send it over PUT, and it'll let you send it over DELETE. Though I'm pretty sure, unless we've screwed something up in the course, that the HTTP standard does ask that you don't send body information over a DELETE too. That's what I mean. These are just kind of standards that people break all the time. Another random example, I don't know if it's in the slides, so in case we kind of cover it later, is we say that, if you're creating some new information at all on the server, right, it should be a post request. But a lot of systems out there, when you go and read a message, update a message, delete a message, create a message, a lot of modern corporate systems will actually be logging something every single time that you make a request. Do you know what I mean? So if you're deleting, adding, whatever, they'll add a line item to a database somewhere that said, Hayden went and did this at this time. So you're kind of always creating something. A lot of systems, if you go and fetch information, they'll be logging that you fetched it. So a purist might argue that every request should be a post request in that scenario, because you're always creating data in some way. But again, there's no firm laws of physics around this. Most people would not do that because it doesn't make sense. So this whole get, post, put, delete thing, it's not like some really technical thing. It's just like people see a bunch of post requests and they go, oh, okay, they're going to be particular URLs that help me create stuff with my systems. And this is where we get into the notion of an API. You've heard me say this word a few times throughout this lecture. And everything we've been talking about so far, we started off with a web server, then we talked about params and bodies and stuff. And then we just talked about put and post and delete. What we've ended up talking about is essentially what you would call a web-based API. And taking a step back from that, an API really just refers to the interface that is exposed by a piece of software. In C, you could think about the .h file as a bit of an API, in a way. It's like the abstraction of the software. And most APIs are there to say, here is a software system. Here is the interface of how you can interact with it. These are the different functions you can call, or in the case of this, URLs. Here's the inputs and outputs you can expect from those functions. Go for it. And most APIs these days are web-based, which makes sense because for an API to be useful to a lot of people, it kind of needs to be on the internet. You don't just have like an API in your friend's garage. That wouldn't really be much use if you're not in his garage. But yeah, web APIs, which are basically just like contracts of how particular services work. Now, random API, we use this service at my job. It's called Intercom. I think I tried to look this up recently, and it wasn't actually as helpful as I wanted. But another one was Canny API. This one's a little easier, I think. We use another service called Canny, which is essentially like a feature request API. It's a system that lets users kind of post features they'd like to see on a product, and then they can like upvote them and things like that. So it's like kind of like a community crowdsourced product roadmap. But it's a service that, whilst they have a website for it, you can also send requests to their API. So if we wanted to, we could kind of maybe create a way that our customer service team could, when a user kind of reaches out on the helpline, they could actually click a button that sends that customer's comments to this system if we want to, right? That's like software developers do. But what you'll notice is that if I have a look through this, this is what an API looks like most of the time. Let's imagine someone's wanting to create their own post, like create a post, a new feature they want to add. So they say, okay, well, this is the URL that you call. That's the localhost 3000/something something. You call that. It's a post one. Okay, post, that means I'm going to be creating something. They have it in curl here, which isn't super useful. You could imagine that as like a JSON object. This part here is kind of the JSON object. They could be like, here's the body that you need to send with it as well in that case. So when we talk about sending that payload, that body that's encrypted, that's an example of it. It's got a bunch of stuff here. This is the post details, the title of the post, a few other random things like who's creating it and things like that. And then it says that once you send that, if successful, the server will respond and give you another object, which is the ID of the post that was just created, so that you can reference that later if you'd like to. And there's a bunch of these, right? It's like a page full of APIs. So a lot of software systems these days built by companies that other software companies use are simply web servers built with something like Express, where all of the URLs in that Express server are given in like a document for someone to read and be able to make a get, push, post, delete request to. Is that making sense? If you're confused, I'd love to hear about it because this stuff can be confusing. Just going to see if there's any YouTube comments. No. And I talked about this at the start, but it's good to kind of consolidate it here. This is how a modern website works. The browser, your phone, your Google Chrome on your laptop, start at the top. It makes a request to a server and says, I'm trying to load Netflix.com. Netflix.com replies and says, here's the web page. Great. And then after that loads, your web browser, as you're clicking next and pause and rating the video and God knows what else, it is quietly sending that data to the server in a series of like, here's an API call to the server, upvote the comment. Like think about YouTube, post a comment, upvote it, whatever else, Instagram, sending a message, liking a thing, commenting on a thing, all of this happening behind the scenes as API calls to a URL, to a post, get, put, delete method, with a payload in some way through the URL or through the body, getting a response that's typically always JSON as well. You know, it's the same thing. So many of these systems are the exact same thing. If we're using this get, put, post, delete method, we refer to these things as RESTful APIs. That's the name we give them. So a RESTful API is one that is get, post, put, delete. There are other types of APIs out there. One of them that comes to my mind is a GraphQL API. I can't say I'm a massive fan of this particular thing. I'm even not going to explain it. I think it's an incredibly powerful way to do APIs for a very specific small number of systems, and outside of that, I think it can be quite challenging to work with. But the point is, if you're like, well, what the hell is another type of API? There's this API. This API doesn't have anything to do with post, get, put, delete. They have their own ways and terms of dealing with things that I'm not going to unpack again. But RESTful APIs, 95% of everything again. It's like vast, vast, vast majority of stuff. Nearly every single API you'll find is going to be the same like that. All right, so we've got half an hour left. And if I kind of just show you this and I skim through it, most of what we're actually going to be talking about is this one here, requests made via code. So we had a web server before, you know, different ways of working with it. We called it on the browser, then we used an API client. But for this to scale and work, we need to be able to send requests to our server via code. So now we're going to write code that is able to talk to the code we wrote that's a web server. So we run a web server, and then we run other code that talks to that web server. It's kind of cool. Here's a really simple example. The library that we're using to talk to another web server is called sync request curl. There are other libraries out there that are way more popular than this and way easier to use in some ways. However, other libraries that do this, they lean on JavaScript's asynchronous programming syntax, which can be very confusing. So we stay far away from it in this course. Has anyone seen online anything to do with the words async or wait or promises yet? A few of you? Don't be scared of it, but it's hard. Like we teach it to level 6 students and it kind of head screws them for a couple weeks. So we figured out a way in this course to just like stay away from it totally. So that's why we use this library, because you don't have to, you know, deal with it. But really simple piece of code. I'll get it up here. Requests. We import the library and we can make a request. We can say I'm going to make a GET request to this particular URL. And in this case, QS means query string. Query string is what you call the stuff after the question mark in the URL. So it's just the query there. And this request is made to that. The server responds and the info is stored in this response object. This part's pretty clean, but the next part's kind of ugly as hell, which is that you get the response object, you get the body of what's been returned. You have to cast that to a string because it's normally a buffer. And then once you get the string, it's a JSON string, so you have to parse that back into a JavaScript object. It's the same line every time, you know? It's a little bit funky and ugly, but it's the same line every time. There's not much problem solving there. And then if I just, which library is that? I got to find our Apple server. There it is, CRUD. That's what I want. So here's our server, and we're also going to use this as a way to kind of toy around with the different methods, because you'll notice here that we have a get URL /apple that takes in data via the query and returns JSON. And then we have a post request called /orange that takes in data via body. That sort of shouldn't be necessary. Okay, yeah, I'll unpack this for you a bit more. So what I'm showing you here is a get and a post that does query and the body, right? They both return JSON. However, we have another example here called CRUD.json, where what CRUD.json does is shows you the effect of changing this from .text to .json, because if you change this from .text to .json, it basically kind of primes the Express server into knowing that you're dealing with JSON everywhere, so you don't really have to decode it and things. And it actually cleans itself up a lot like this. You saw this example before with the response, but what you'll also notice is that without that .json part, things still can work, but because the bodies you send are based on JSON, you then have to parse that as well, and it just gets a little bit messy and it's easy to miss stuff. So we always try and do our Express servers as with that JSON part there. So this is our nice server that we're going to run, and it's a server that we're going to test because we have our Apple. It's running on port 3001, npm run ts node crud.json.ts. Now it's running, sort of, not going to run cross.json. That's wrong. Cool, it's running on port 3001. Now we want to test it. So what are we going to do? Well, we have our, where is it? Request.ts file. And I'm going to go open that in another window. I don't know why it couldn't do that for me, but that's OK. And I'm going to run npm run ts node request.ts, and it needs to be what the hell? Let me just check what's wrong there. Sync request. Oh, OK, I have the wrong library. Ignore me. That's probably going to screw up. Don't ever do what I did. The best thing to do if you have the wrong library is not to go change the name, because you'll screw up all the versions and it won't make sense. So the right things to do is to simply install it like that. So we give that a sec to install. Shouldn't be too much of a hassle. It's installed. Now I run it again, and you'll see that it gets that back from the server. Now, to make things really clear for you, I'm going to go put a console log in here, just so you can see, calling Apple. I want you to kind of really see how this is working. Because I've changed the server, I need to stop it and restart it. It doesn't just magically notice the code changes. When you run the server, it takes the code off the hard drive, pulls it into RAM, and then it runs it in RAM. So anything that happens on the hard drive, it's obviously not aware of it. And I run that again. You'll see every time I run it, it doesn't print anything because that's the wrong file. This is the right file. Got to restart the server. So when I run it, it should print out calling Apple. So you can see the server is receiving these tests as they're coming through, right? I'm just like spamming this at this point. And it'll just like, and this is what a normal web server is doing. It's just sitting there all day, getting requests, sending stuff back. If I change that from Apple to Orange, it would do that. And here is a slightly more thorough test, which I'm using in Jest now, right? So this is now me tying in what you know about Jest with this kind of structure, because you know how to write Jest, right? I hope by this point, if you haven't figured that out by now, you're pretty screwed for iteration 1, probably, but it's never too late to start. So you've played around with Jest. Describe test, it's just that instead of calling a function and doing an expect on the response of a function, I'm just gluing what I already know about making HTTP requests here. This doesn't matter for iteration 1. None of what I do today does. If you haven't figured that out, I'm sure you have. This is all about iteration 2 next week, because once you get your iteration 2 next week, you're going to be converting your functions to web server routes, and the stuff you built so far will become the basis of a web server, and you'll be testing that web server. The good news is that because you've already written a lot of the tests, a lot of the tweaks and things to make it work are fairly cosmetic, you know? Like it's not a lot of problem solving again. It's a lot of just getting these things set up here, because you probably got all the describes and tests. It's just right now your stuff probably looks like the equivalent of me saying, you know, const response equals apple. Expect res to be apple. You know what I mean? Like that's kind of what you have now, or some equivalent of that. But to do HTTP, you just need that extra stuff there. Similarly, you could test orange as well. If you wanted to test it with the body, you would have to change this from get to post. It depends what's in the file. You can see it's a post request, cool. And I'd have to change query string from that, from query string to body. And then I could probably do name.Hayden there, and then we could try calling it as well, see what happens. Oh no, we get an error. This is another problem with this, is that when we send JSON with our request library, we do need to, oh actually, let me try this first. I don't remember if this works. I doubt it does. Maybe it does. Oh, it does, there you go. Well, I just saved teaching you all the wrong things. So JSON is a proxy for like the equivalent of like body, but it's sent as JSON. That's what JSON means there. So if I had body and I made this as like JSON.stringify like the other stuff, that is equivalent to this. So I'm just sending it over the body, and you see that works as well. So I can send put requests, post requests with information passed through the body. I can send get requests, delete requests with information passed through the query. They all return JSON, so I'm all capturing them back this way. And then we'll see if my jest works here. npm run request json.test.ts. I don't know if jest is set up. It looks like it is. There you go. So that's how you run jest with it. Now this is important. For your jest test to work, the server needs to be running. If I stop that server and I run this, jest just tries to talk to the server, and it's like nothing's there. So the test will fail. You don't need to worry about that in terms of the pipelines. We sort that out for you. It's more like when you're testing these things locally, you do need to actually run the tests as well. This is also one of the reasons we actually got your clear functions and stuff implemented, because you would, just like in iteration 1, clear these tests before you run them, because sometimes your server might be like running amidst many, many tests. So Ghosted Blade says, will this be covered in more detail next week? I'm still really confused about all of this. So what I'd say is like, there's not actually like a lot more detail to cover. We've actually gone in quite a lot of detail today, but that doesn't mean it's easy. There's a lot of new ideas here, right? There's actually like not any extra syntax to unpack, or there's not like any other parts of, you know, Express that are really critical to do stuff. All you really have to do from here is like get stuck into your week 5 lab next week, which has a lot to do with this. And your iteration 2 that comes around next week, you start to do this as well. And you'll also see more and more examples, I believe, will, you know, be included with Express servers. But what I would say is for the typical student here, there's not really like a whole bunch more detail to unpack. It's more like you learn this stuff, 2/3 of it makes enough sense, 1/3 of it's still a bit weird. You'd have zero confidence in doing this yourself. So you go, okay. And then you finish iteration 1 this week. Sure. Then you get started on next week's lab. You do the lab a little bit. You do some of the other activities. You start to get it a little bit more. You go reference the lecture slides, maybe the recording a little bit. Starts to glue together more. You do the lab. You start doing iteration 2. It's just like a typical teething thing. It's a little bit like Git. You know, like what we taught you in week 1 in Git, or what Yuchao taught you, probably made no sense in week 1, right? It's like a little bit confusing, all the like gits and merges and branches and stuff. If you kept up with it, you're like quite smart, because a lot of us struggle with that. There wasn't really much more to unpack. You just had to kind of do it for a bit, right? And now I bet you're in week 4 and you're all like Git magicians by now, right? Yeah? Everyone's like, no. But it's like, you know, you're like, okay, I got to make a branch, and then I got to commit, and then I got to make a merge request, and I got to put it back. You're like, okay, I kind of get the gist of it now. So obviously there is like more that we'll continue talking about it, but a lot of it's here today. And as you do it, it's a hard thing to learn without doing. So as you do it, you'll start to understand more of it. Now, that was a bit of a ramble about the request library. Working with Jest, we already kind of talked through that example a little bit there. One thing I would say with Jest, though, is you can abstract stuff too. So if you pay attention to this test we have here, we've got a lot of repetition for GET requests and POST requests. Many of you are going to do the same thing, which is you'll realize that a lot of your GET requests and POST requests look the same, and you'll go make yourself some like helper functions like this. You know, because if you're making like 10 GET requests, there's no point copying and pasting the same URL, the same GET string, the same query string, whatever. So this route, this function, all it does is says, well, I'm going to make a GET request, and it's just going to like be dynamic based on the route and that particular query string object we're passing through the URL. Because remember, this query string here, like if this object, for instance, was like A is 1 and B is 2, it's the equivalent of coming up here and doing that. That's what the query is, for those of you who've like not linked that together. It's just that the request library does that for you. You give it that object and it goes and shoves it in the URL for you. If you really wanted to, you could actually skip that whole thing and just like put stuff directly in the URL. It's just hard to code and a bit messy and things like that. So the object's quite nice. But the point is that you might make these helper functions like this. So for those of you who looked at that and thought, oh my God, my tests are going to be like wildly complicated, that's okay, because you'll end up with small tests like this, because what you'll end up with eventually is some kind of like body is just get apple, there's what I'm passing into it, and then I just compare the response. And this is kind of why I point out again that part of iteration 2 where you're just kind of taking what you've done in iteration 1 and making it more web servery is just a lot of code fiddling, really. It's sometimes we refer to it as like boilerplating again, where you're just not solving problems. You're mostly trying to battle syntax, not algorithms or data structures, which to some people can be kind of annoying. Other people find it relaxing. It kind of depends who you are. Some people like that like just reorganizing code element, and some people like really, really hate it. So I've kind of summarized what's written up here. Many of the routes in iteration 2 are just wrappers of your iteration 1 functions. Therefore, it should be easy to wrap your iteration 1 functions in HTTP servers, etc. There is a lecture on iteration 2 next week. So the only kind of other HTTP stuff to unpack is probably more like during that iteration 2 lecture next week, we'll probably grab some examples of iteration 1 and just like show how you'd convert it to iteration 2, just to give people a bit of a confidence boost. Because sometimes it can be hard to like relate all these like apple, orange examples to something that's more, to do with the project. So there's a couple of important facts, and then we're kind of done. This one's pretty important. So in iteration 1, if there was a problem, you would return an error object, right? Right? You'd like return the actual object, or you'd return some object with error and then the error string. In iteration 2, and we'll talk about this more next week, but it's just explaining it, is the way you return errors is actually by returning a different status code, like this. There's a little bit to unpack here, but basically when it comes to HTTP stuff, web server stuff, they have a standard way of describing how successful a program is. We know this like in Bash and stuff, 0 means success and 1 or others means failure. But with servers, they have a thing, HTTP, they call them, I don't know if they're called error codes, response codes, sorry. They have a whole bunch of different response codes. It's a really long list. But we only ever really need to worry about a couple of them. And this is all well described in iteration 2. But one of the most common ones you'll see is this 400 one. A 400 basically says that the server can't process the request because something that has been sent to it is wrong. It's pretty much what a lot of the errors are in iteration 1, right? Like someone tries to register with an email that's already registered. Someone tries to change their password, but the password's wrong. So the point is, for anyone who is thinking far ahead, imagine that for a second. really. You had like app.post auth/register. Imagine you're doing like, iteration 2 conversions right now. And previously, I don't know what you'd have here. You'd probably have a function that's like, capture the auth user ID. Oh, I'm sorry. Something like this, equals admin auth register, where you pass in like request.body.email, request.body.name, or .password, right? Like this is kind of an example of how it might look in iteration 2. And then here you say like return response.json, auth user ID. Now, the point I'm getting at here, and again, we can talk about this next week, but this is an example of how you might kind of reuse what you've done in iteration 1 to like wrap it in an HTTP server. Because all the logic about checking emails and passwords, that's all kind of going to be behind this function here. Because that's a function you've already written now, right? Most of you have written that function and finished that function. Takes in an email and maybe I'll make that login to make it more accurate. It takes in those two things and it does stuff. But let's imagine for a second that the password's wrong. So maybe you end up having a check that's like, hey, if request.body.password.length is less than 8 or whatever it is, normally you might say return error password length bad, right? For iteration 2, how we deal with these things instead of that line is we simply say response.status 400 I'm just trying to think. We kind of ummed and ahed about doing this, but don't worry. Is you return the error just like you normally would, but you also attach this status part to it. I'll double check with you, Chow, because we've had a couple of terms where we've ummed and ahed about pushing that status part to iteration 2 or 3. I'm not running the course this term, so I don't know exactly whether that was in iteration 2 or 3. So if it's not in iteration 2, I'll get you, Chow, just to clarify that in the weekly notice. But for now, I'm just going to assume it is. This status code will depend on the message. It's either 400 or 403. This is well laid out in iteration 2, though. It's not really something you need to worry about what numbers are there, because we kind of tell you. But it is something you have to add to it, too. Because naturally, you are kind of sending that JSON message back with the error, just like you do normally. But you will also send this status code back as well. The status codes are how you kind of tell what's going on. Because in generally speaking, how it works is like anything that starts with a 2 means like the thing went okay. Anything that starts with a 4 means that the client, the person who made the request, screwed something up. Anything that starts with a 5 means that the server screwed something up. And they all kind of have different meanings underneath that. But again, we only really focus on a couple of these in the course anyway. So we will kind of see more of that. That'll make more sense when you look at iteration 2. A couple of other express helper things. Sometimes you'll see in routes that there are versionings in the routes, like v1, v2, v3. This is quite common because what happens in the big world is someone will have an API with like 20 routes, like that Kenny thing you saw before. But what happens is, like v1 here is a good example. Kenny comes along and they say, we've got a whole new API. It's really different. It's much better. It's much faster. And it has different inputs and outputs. But they can't just replace their API because there might be thousands of people using this thing. So what they do is they create a second API docs that has v2 in the URL, just so everyone knows what version it is. And they keep both of them alive for a long time. And everyone who's using v1, they send them an email and they're like, you got to stop using this. You got like 2 years, 3 years, 4 years, and then we're going to shut it down. And they'll run those two things in parallel, and then it's like gone forever after that point. And by then, maybe they've moved on to v3. So that's just more like an FYI background knowledge. That's usually what versioning in URLs is for. We do a little bit of this in the course as well. A really random note to point out, but actually, that won't really make a lot of sense to you right now, probably. But you have to just be careful sometimes when it comes to route definitions, because like what can happen with servers is that if you have a route like this and you have one that's like Apple and it takes in a name, And then you have another route called apple, which are different routes because one of them is like apple / something, and the second one's just / apple. Is that if you do apple / something, if someone tries to call / apple, the URL, what can actually happen if you order them that way is this first URL says, hey, I can match that because that looks like / apple / nothing. You know, so like normally / apple will match that. So if you ever do have URLs that look really similar, just be really careful about how you order them. But again, this is like a 1% of students run into this problem, so I don't really want to dwell on it. A tutor's just asked me to put this in the slides, but I really wouldn't give it too much thought at the moment. And this stuff is pretty nuanced. We can maybe talk about it next week when we talk about iteration 2. But I don't think these last slides will go into any great depth with. So just to recap, okay, so recapping things pretty quick. What we've talked about is all of HTTP servers. We've given a little bit of the conceptual background. We've shown you how to make an Express server with all the different ways you can tweak it. We've used really simple examples. And then we've shown you how to test a web server. So you've got all that basic knowledge now. The main things for you to go and do are to go and actually work with it in your labs and your project. And in our lecture next week where we talk about iteration 2, we'll unpack some of this too. And hopefully by then, because you've looked at it, you're going to have some more questions and we'll be able to have a bit of a better discussion and fill in those last bits of gaps about it. And we can talk about some of those other slide elements later. But that's the main stuff. Now, a question came up in the chat about linting. Will we cover linting in this lecture? No. So there's no time this week to talk about linting. As I understand it, Yu Chao didn't get to linting last week, and I think Yu Chao is going to send out a video about linting on Friday. So that's the case with linting. But yeah, thank you all. Have a great day. I'll see you Wednesday next week, I think. Thanks for putting up with me again.